Hi everyone. This series of videos isn't really going to teach anything new, but instead we're going to build off of what we did in the previous set of videos, which was the snow accumulation question, where we really tried to make some pretty crucial links between the functions that we're given, which is usually a graph called little f of x, and the function that the problems want us to analyze, which is capital F, not exactly related to the graph. So this connection between capital F and little f on these problems is really an extension of the second fundamental theorem of calculus, but most importantly, it's a question that we often end up seeing. This interpretation of big F through the lens of little f is a very common AP style question, and it's a question that really brings in nearly everything we've ever done this year in calculus. It's all of the function analysis that we learned first semester, so words like increasing and decreasing will make a comeback. Words like minimum and maximum, concave up, concave down, those are definitely function analysis words. But it also brings into mind our understanding of integrals, specifically integrals as areas, since you can see that this function is a geometric style shape, but definitely doesn't appear to have any sort of integral function that we can take an antiderivative of. So you can tell how we're sort of marrying the two main ideas from the year, and that's why this is often presented as the culminating topic, the last topic that we really attempt to look at in depth in calculus, because it attempts to marry the two semesters together. Everything that we know from analyzing functions in first semester combined with everything that we now know about integrals from second semester. So this series of videos is going to take you through question number 14 in a series of parts, figuring that this example can basically stand for virtually every question from page 14 all the way to page 20. You'll actually see a lot of similarities if you start flipping through the packet and look at some of the pages between 14 and 20, because virtually all of them have the exact same setup. They give you a graph. They're going to ask you to analyze a function called big F that is related but not directly to the graph. And then they're going to ask you to do a whole bunch of function analysis like concavity, increasing, decreasing, min and max, in order to show those connections. We'll start with letter A, figuring that this is usually the first step in a function analysis type of problem. Get familiar with the function that they want you to analyze. In letter A, they want us to analyze the function big F. Now it will be important to keep clear which function is big F and which function is little f, because the naming convention that they use is definitely confusing, and we don't want that to interfere with our ability to do the problems. Big F, which I'll highlight pink here, is the integral function. So big F is the integral from 0 to x of little f of t dt. The little f function is referring to the graph. So I'll just make sure that it's absolutely clear. Little f is going to be the graph. Big F is going to be the integral function. When we do each of these problems, we'll need to make sure that we're looking carefully at which function they want us to work with. For instance, in number 4, letter A, part 1 wants big F of 0. So that means we're going to have to look carefully at the big F function in order to calculate this value. Now, since big F is an actual function, I can simply find big F of 0 by plugging 0 into the big F function wherever the letter x is. Remember, there is an issue with the dummy variable situation, but it should be noted that anytime they give you an input here, they're giving you an x value. The t in the dummy variable ends up working itself out, as you saw in the last series of videos. So big F of 0 is, if I copy out the function, the integral from 0 to 0 of little f of t dt. Now I'm looking at this, figuring that I just need to figure out what that integral is. Remember, we don't know what little f is as a function. All we know about little f is that it's an area under some sort of curve that they gave us in a picture. So we're going to interpret all things little f right now, all integrals with little f, as area problems. So I'm going to interpret this problem as the area on the picture starting at 0 and ending at 0. Now, of course, if I look at this picture, and start at 0 and end at 0, I go nowhere. There's literally 0 area to find. So big F of 0, I can say conclusively, must be 0 because there is no area in that region. Now, of course, some of these questions will indeed have an actual area to do, so that's why I'll do another example. This one was a bit trivial. In part 2 of the same problem, big F of 2 would be, and again, I'm just copying it out from the big function that they gave us, the one I highlighted pink up at the top. Big F of 2 is the integral from, and I'm copying the function, 0 to 2. I plugged in x where the letter x in the formula was, and then f of t dt with its dummy variable that we know we don't have to worry about. This again, I'm going to interpret as an area from 0 to 2. Now that actually seems to be a little bit more interesting. If we look at the picture, the area from 0 to 2 must be referring to this little semicircle in this region. So now I need to find the area of a semicircle. Now, it's actually a little quarter circle when I think about it. The semicircle goes from 0 to 4, so I have a quarter circle that I need to deal with here. Let's think geometrically about how we could do that. The area of a traditional circle is pi r squared. And since this is a quarter of that circle, pi r squared divided by 4 must give me the answer that I need. So I'll look at this as a full circle, assuming it was actually all there and I just don't look at the bottom half. The radius appears to be 2, so 2 squared is 4. That means the area of the full circle is 4 pi, but divided by 4 would be 1 pi. So I know that the area of this semicircular region is 1 pi. Now, in terms of positive negative, which is always smart to analyze, it looks like from 0 to 2 I'd be heading towards the right, which is positive, and I'd be heading up to fill in the rest of the area, which is also positive. So while it's not traditional to think of a circle as having a positive or a negative area, pretend you're just doing any sort of triangular or rectangular shape and just go through the same motions. To the right for the base is positive, up for the height is positive. So even though it's not a traditional base times height, it's still a consideration that you can make. Positive times positive yields a positive area. So the area from 0 to 2 is positive pi. Now, of course, the rest of these are going to kind of end up being similar. So I'll do a couple more just so you can see the flow, and then hopefully you can do the second row, which is parts 5 through 8, in a similar fashion. Big F of 4, I know is just the area from 0 to 4. So you don't have to copy out the function every time if you don't want to. You can even do yourself a favor and write it in words. You could even write area from 0 to 4, if that helps you understand it better. You can, of course, keep using calculus notation as the integral from 0 to 4. Do whatever makes sense. Ultimately, you're just finding area. So if I go back to my semicircle here, the area from 0 to 4 really does fill the rest of the semicircular space. So since I already know that 1/4 of the circle is pi, that must mean that the 2/4 of the circle is another pi, which means in total the area from 0 to 4 must be 2 pi. Now this is where some people start kind of color coding their different regions so that they can tell which is which. That's always a good idea, especially if you have trouble keeping straight on these tiny little pictures all of your details. So just think about what works for you, but definitely don't be shy to color things in or to make it your own if you can. So again, just to recap, the area from 0 to 4 is pi plus pi, which is 2 pi. And we'll just continue on. Now the next one is the area from 0 to 6. Big F of 6, if I put that in the integral, would say the integral from 0 to 6, which I'm interpreting as the area from 0 to 6. So now I'm going to look at the entire area from 0 to 6, which I already know is a semicircle plus this little triangular region. So now I want to make sure that I focus on this little triangle as well. And I have to make a note to myself, this is probably not going to be a very nice number because a triangle is not going to have an area in terms of pi. So I'm just going to have to do the best I can. Assuming I'm heading from 0 towards 6, The base would be a positive 2 on this triangle, because of course, moving to the right. The height would be negative 2, because I'd be going down, hence the negative. And a triangle's formula is base times height divided by 2. So 2 times negative 2 divided by 2 would give me an area in this triangular space of negative 2. So color coding or doing something like this could be helpful so you can keep it straight, because at this point, now we have 3 different regions that we have to add up in order to find the total area from 0 to 6. I have pi plus negative 2, and the only clean way of writing that, if we don't want to get into decimals, is to simply call it 2 pi minus 2. You can turn it into a decimal if you want to, but it would never be expected of you. And even though you can use a calculator for the AP test, they are still certainly fine with you leaving things like this unsimplified, because the point of these questions is to just quickly get a value, and you don't usually have to do anything with it. So simplifying it in a calculator is just a few extra seconds you don't need to spend. Now, almost all of the questions in the second row are duplicates of what you saw in the first row. So between now and the time you take the next video to start, try parts 5 through 8, which is big F of a series of additional numbers on the left-hand side of the picture, to the left of 0. For all of these parts, just make sure that you're starting your integral at 0, because that's what big F function tells you. The big F function says you're starting at 0. So if you're going from 0 towards negative 1, pay attention to that direction. It'll have a negative base because you're starting at 0, and big F told you to do that. It's not because we always start at 0. We always start where big F tells us. So since big F tells us to start at 0, you are obligated to do so. In the next video, we'll talk about part 9 in this question, which does start to take on a bit of a twist.